1 minute stop. Okay, one your presentation. Right. Thank you very much.
Thank you so much. Okay, yes. So our next presenter is Dr. Timothy Raupak, and he's going to talk about recent trends in proxy-derived hail hazard in Australia's major cities. So over to you.
Okay, thank you. Hi, I'm Tim Raupak. Thanks for being here. And for those people who've travelled from a long way away, welcome to Sydney. I walked from downstairs, so I kind of cheated.
Very local.
Yeah. So I'm going to start locally. Oh, before I start, I'll just say this is work I've done with Joshua Soderholm, Rob Warren, and Steve Sherwood. Joshua and Rob are at the Bureau of Meteorology, and Steve is here at the Climate Change Research Centre, where I also work. So I'm going to start really local here. This is an aerial photo of where we are now. So this is the UNSW campus up here. Here are our nice beaches. I hope you get a chance to visit. And down here is a suburb called Kensington, and it has all these blue tarpaulins on the roof. And the reason that those tarpaulins are there is because there was a hailstorm in 1999 that came and smashed all the roofs. And this was between certain years, but many years, 1966 to 2017, it was the most expensive insured loss event in Australia. And it remains so to this day. It's only challenged by the floods that we had last year. So hail causes an enormous amount of insured losses. It really drives losses every year in Australia in terms of the insurance industry. And so just to put that in perspective, over this same time period, hail caused more insured losses than bushfires and floods combined. And we have quite a lot of bushfires, quite a lot of floods, yet hail caused more insured losses. And this is often because it hits cities. So a couple of years ago, I led the writing of a review paper which kind of tried to put into one paper what we know about hailstorms and climate change. So this was published in 2021. And I had a great group of authors there. There were 9 of us from all around the world. And here's the kind of overall picture that we decided was the state of knowledge at the moment. Hail is expected to be affected by climate change, but there's really high uncertainty on how those effects will come about, and really large geographical differences in both the observed trends and the model trends that we see across the world. And then here I'm looking at Australia in particular. So just to dive into a little bit more about how that works, to get a hailstorm, you need a thunderstorm, of course, so you need an unstable atmosphere where you can have an updraft forming. The updraft pulls moisture from near the surface up into the atmosphere. When it gets above the melting level height, which I've written as MLH here, that's where the temperature is below zero, and you get ice formation and you get supercooled liquid forming. So that's water that is below freezing but still liquid. And when that water hits little ice particles, it freezes to the outside of those particles and it starts to grow. And this continues and continues until the hailstone is so large that the updraft can no longer hold it up, and it falls. And it falls down below the melting level height, and it melts between that height and when it gets to the ground. So in a warming climate, there are 3 main changes that we could see that would affect these processes. The first one is that in a warmer atmosphere, the atmosphere can hold more moisture, and therefore there's more energy to be released. And so there's more instability and perhaps more of a chance for updrafts to form and to form larger, more intense storms. The second one is that, of course, there's more melting in a warmer atmosphere. It's just warmer, and the melting level height will be higher, and that leaves more room for hailstones to melt between when they fall out of the storm and when they reach the ground. And they might melt away entirely, just form rain, or they might just get a bit smaller. And the third one is vertical wind shear. When there's lots of wind shear, so lots of difference between the wind at the ground and the wind aloft, then the storm gets more severe. We think overall wind shear might be reducing, but there's a caveat here because at the time that hailstorms tend to form, there might be an increase or there might be changes that are just overlaid by the changes in instability. Instability is a more important factor. So overall, we say that the very broad expectation, if you just look thermodynamically, the broad expectation is for a reduction in surface hail frequency because of this increased melting, but an increase in severity because when there is a hailstorm and when you do get hail at the surface, it's likely to be larger stones that survive that increased melting. But I want to stress that there's really large geographical differences, so there's very high uncertainty still globally. So now looking to Australia, we worked on making a new proxy because often we don't have observations. It's hard to make models of hail that run at a continental scale at convection permitting resolution. So we're using a proxy in this study. And what you normally do with a proxy is you take your environmental factors. So in this case, it's wind shear and instability. And you'd say, well, if we've got a lot of instability and a lot of shear, then we've got a hail-prone environment. And if we don't, then we don't have a hail-prone environment. And what we've done here for this new proxy is we've actually allowed for this line to change depending on the environmental conditions, which we use melting level height for. The reason for that is because we noticed that across Australia, there's this latitudinal difference in environments. So closer to the equator, you have a lot more instability. The melting level height is higher, but less wind shear. And it all reverses as you go further to the south. You have more wind shear to the south, but less instability, but you do still get hail forming. So what we allowed to happen is for this line to change based on the melting level height, which is like a proxy itself for the latitude in the country. But it's an environmental proxy, not a spatial one. And this has been published in Monthly Weather Review this year, if you want to find out the gory details. When we applied it now to Era 5 reanalyses, which go back to, we're using data from 1979 when satellites were added to the analyses. And here I've applied it to 3 hours through the afternoon. So 3, 6, and 9 UTC, those are afternoon hours across the country here. And this is the climatology that we get for where we get the most hail-prone days. And it lines up with where we expect to see it. In Australia, we do get a lot of hail along the east coast. Over those high population regions, we get a little bit in the west over Perth, and over the north and the centre we don't get so much. So it lines up with what we expect for the country. It also lines up with where the population tends to be. This is just kind of bad luck for us. We built our cities in hail-prone locations. And now I'm going to go to trends, looking over that same time period. So here I've marked the cities. So these are the major cities in Australia, and they also happen to be where we're seeing increasing trends in hail-prone days. So we do see a decrease over most of the country, including especially in southeast Queensland up here, and over the interior of the country and to the north. But over some of the major population centres, like Sydney, Canberra, and Perth, we see an increase in the number of hail-prone days by about 3 days annually per decade. So you might think, well, is that a lot? Is that little? So here I'm zooming in to the cities, and I'm showing now in relative terms. So this is compared to the mean, so the climatological mean, and it's per decade. So what we're seeing is that over cities such as Sydney, Perth, Canberra, we're seeing about 10% per decade, so about 40% of the mean over that whole time period, 4 decades. And over other cities like Brisbane, we're seeing a decrease. Melbourne and Adelaide, we're seeing decreases. And on these maps I'm showing, it's probably hard to see, but in the fuchsia lines, these pink lines, that's the outline of the significant urban area. So you can see that this is where there's a lot of assets that are exposed and a lot of people that could be hurt by increasing numbers of hail-prone days. So Brisbane's interesting here because overall we're seeing a decrease, but actually when I break it down by season, we see that in most of the other cities, the signal is roughly the same across all seasons. But when we look at Brisbane, we're seeing a decrease in summer, but a big increase in winter. So I think there might be a seasonal shift that's happening here, where we're seeing more wintertime events occurring. And the signal tends to be quite strong in winter and showing increases or decreases, but it generally is stronger in winter. There might be a seasonal shift. So what explains these trends? Here I'm taking apart the different ingredients that go into our hail proxy. So we've got CAPE here, that's convective available potential energy. That's a measure of instability in the atmosphere. Lifted index is also a measure of instability, but its sign is reversed from CAPE. This is shear. This is the melting level height, the lapse rate, and the temperature at 500 hectopascals. So to no one's surprise, Australia's getting warmer over this time, so we're seeing an increase in the melting level height and the temperature. Over the shear, we're seeing decreases across the north, not a lot happening in the south. And the interesting one that I really want to point to is the instability indices, which show trends that match with our hail-prone day trends. It's getting more unstable in the southeast, southwest parts of the country where we're seeing more hail-prone days, and it's getting less unstable in the north and in Queensland where we're seeing decreases in the hail-prone days. And indeed, when I then try to actually take out the effects of those ingredients, here I'm showing the effect on hail-prone days when the trend in the mean of these ingredients has been removed, and it highlights where those ingredients have particular effects. And so we see that the trend is mostly explained by instability, especially where we're seeing increases, also to some extent where we're seeing decreases. So really the big driver of these trends is changes in atmospheric instability, so the propensity for storms to form and the strength of the updrafts. So we've used reanalysis data for these, but we did compare to radar data to get some other comparison to try to understand whether the trends line up with another data source. So here I'm comparing to the longest radar time series across 6 regions in Australia. I should point out that the longest radar time series is about 20-something years. It's about half of what we see in the reanalysis data, so we have to take that into account. But I've aggregated to the same points and to the same time so that I can compare apples to apples. And here is a comparison for Sydney, for example. What you see here is that the proxies, the signals co-fluctuate very well, and we see an increase in both, but there is a large difference between the number of hail-prone days that are detected and the number of days that actually had hail detected by radar. That's to be expected because actually most of the time in the atmosphere, when you have an environment that's really prone to forming hail, you don't get much hail. So it's just one of those problems. It's called the initiation problem. It's hard to determine when a hailstorm will actually happen. But we can still talk about relative changes in the environment and know that it relates to relative changes in the actual number of hailstorms also. Okay, so that was my last slide, so it's about time for me to wrap up. Thank you. Please reach out if you have comments or questions.
Thank you so much for your talk. Okay, there is a question, please, from the back.
Really interesting talk. It's very provocative to think that the urban area will have a feedback in this. But I was also noticing that you have a certain latitudinal gradient below which you start seeing that signature along the different cities. So, do you see anything in the context of the ocean temperatures that may be causing a change in the